Welcome, geometry students. Today we're taking a look at our review worksheet for Chapter 11, running through the 15 questions that are a part of the worksheet. So let's get started in the first problem. Find the indicated measure. Number one has us looking at the circumference of circle F. So this type of problem, along with the second problem that's also on the same slide, have us working with the same proportion, and that proportion is the proportion that looks like this. It should be arc length over circumference, we'll just label that as a capital C, is equal to arc measure, that's always written as a degree measurement, divided by 360 degrees. Okay. So to set that up for problem number one, since it's the circumference that we're trying to find, it's the first denominator that would be left as a C. We do know what the arc length is. That's labeled as 64 inches. So that will go in the first numerator. We'll leave a C in that denominator. Arc measure would be the degree measurement going along with that arc, which is 210 degrees. And that gets put over 360. I will skip the degree measurements, degree symbols, because they're going to cancel each other out anyway. So if I were to make a quick calculation on my calculator, I literally would take 360, multiply it by 64, and divide it by 210. So as for work that I would look to see on your test, I would be looking for this proportion. So this is the kind of work I want to see. And your answer there for C is approximately, we'll round to one decimal place throughout this worksheet, 109.7. And we'll get the right label on that. And the right label on that would be in inches, since it's a linear measurement. Okay, now if I can come up with exact measurements, I would give exact measurements, but that one, I guess I could get a fraction for my final answer, but in this case, rounding it to the nearest tenth was just fine. Okay, so same type of problem, same type of proportion, but I'm looking for the arc length, which is what makes up the first numerator. So my first numerator is going to just be an X because I don't know the arc length. So I want to know how long this is. That's what it's asking for. So the denominator of that should be the circumference. And circumference formula, kind of an aside here, circumference is 2 pi r. I'm going to replace r with 27, so C equals 2 pi times 27, which gives us an exact value of 54 pi. So 54 pi goes down in that first denominator. Arc measure takes up the second numerator, that's the 75, and 360 always goes down below that. Okay, so if I'm going to punch this into my calculator to get an exact value for X, I'm going to punch everything in except for the pi. So I'm going to punch in 54 times 75 divided by 360. And in this case, I will hit my math, enter, enter, to get 45 over 4, and I'll tag my pi along with that. So, whoops, 45 pi over 4, and I know that we were measuring everything in feet here, so this would be in feet. If I want an approximate answer rounded to the nearest tenth, I would just multiply that answer by pi, and my approximate answer to the nearest tenth would be, whoops, 35.3 feet. And that is question number 2. Okay, moving along to the second slide. In the second slide, questions 3 and 4 are asked there to find the area of the shaded region. And number 3, the shaded region is a sector. So we have a similar proportion to what we were using back in question 1 and 2, but the left-hand side of this proportion changes to sector area over area of the circle is equal to arc measure over 360. Okay. Oops, I probably could make that fraction bar a bit longer. Okay, so that's what I'm going to fill in order to complete question number 3. So sector area is what we're looking for because that's the blue shaded area. So that, since I don't know what stays in X, the area of the circle, we'll kind of do an aside here, area is equal to pi r squared. The r value is the 8 inches that's given in the problem. So area is equal to pi times 8 squared, which is 64 pi. So 64 pi takes up that denominator. Arc measure, that's what the 255 is doing on the outside. Again, I can skip the degree symbol because between the 255 and the 360 I put down below it, they would cancel each other out. Okay, let's come up with an exact value. In order to do that, let's do it on a calculator. I'm going to enter in everything except for the pi. So 64 times 255 divided by 360. And if I hit math, enter, enter, I get 136 over 3, and we'll take pi along with that. 136 pi over 3, and everything there would be measured in square inches. And if I want an approximation, multiply that by pi on the calculator. And when I do that, I get a rounded answer of 142.4 square inches. It's 142.4 square inches. Okay. There we go for that problem. That's number 3. Moving on to number 4. Number 4 actually has us working with 2 geometric shapes to find the area inside the rectangle but outside the circle. So if I was setting this up as a area problem, I would say I'm looking for the area of the rectangle minus the area of the 2 circles. Minus area of circles. So let's get some formulas involved with this. So area of rectangle would be length times width. Area of circles, there are 2 of them, so 2 times pi r squared. So the length and the width. If the radius is 6, that actually can help us with the length and the width. So going from the lower left corner to the lower right corner, I would consider that to be my width. And that would be radius plus radius would give me a total of 12 feet. Length is going up and down. And if I go all the way up and all the way down, you're including 4 radii put together. So I call that my length. And that length would be 24 feet. Okay, I think I have all the numbers I need. So 24 times 12 minus 2 times pi times 6 squared. So if I'm looking for an exact value, I'm going to get 288, that's 24 times 12, minus 6 squared is 36, times 2 is 72 pi, and that would be in square feet. And if I enter that into my calculator to get a rounded answer, I would end up with, to 1 decimal place, approximately, let's make sure this is an approximate symbol. And that probably doesn't look super good, so let's try that again. And that would be 61.8 square feet. So again, that 61.8 is coming from taking 288 minus 72 pi and rounding to 1 decimal place. Okay, on to our next slide. Questions 5 and 6 are on this side, looking for the area of the given polygon. Kite has its own area formula. Kite formula is 1/2 diameter 1 times diameter 2. Let's not call them diameter. Let's call them diagonal 1 and diagonal 2, though. So kite area formula is 1/2 diagonal 1 times diagonal 2. So the 20 centimeters is hitting this up and down diagonal. That's where the 20 centimeters is coming from. We can call that diagonal 1. I don't know why diameter is in my head right now, but diagonal. Okay, the 8 looks like it's half the other diagonal. Let's put 2 8s together and actually get this diagonal 2, to be 16 centimeters. Okay, so here we go with our 2 diagonals. The area of the kite should be 1/2 times 20 times 16. And half of 20 is 10. 10 times 16 gives me 160 its area. So let's go with square units. And 160 centimeters squared should be a good answer for the area of the kite. Again, that area formula, 1/2 diagonal 1 times diagonal 2. Okay, regular heptagon. Heptagon has 7 sides. The area formula for any regular polygon is this. Area is equal to 1/2 times our apothem times the number of sides times the side length. And this is a super duper nice problem in that direction because this heptagon has all the necessary information provided on the diagram. So let's start with what we call the apothem. The apothem is the measure of the distance from the center of the shape to one of the sides. And if we're looking at the distance from the center to one of the sides, it's always going to be a perpendicular distance. So this 21.8 really is our apothem value. S represents the side length, and that's what the 21 represents. And since it's 7 sides, then we actually know that N is 7. And that takes care of all the necessary pieces. So let's just plug them in. So 1/2 times 21.8 times 7 times 21. And when I look at those numbers being multiplied together, we can plug it into our calculator. And I think we should end up with an exact value here. Anyway, this is an exact value, plugging all those numbers into our calculator. Let's just plug them in. So 1/2 is 0.5 times 21.8 times 7 times 21. And we get a grand total of 1,600. And 2.3, we don't have any label on in terms of units. So let's just call this units squared for our label. That's what I would do in number 6. Okay, so on to number 7. Number 7 is still a regular polygon, but in this case, it's a hexagon, which has, you can count up the sides, 6 sides. So that automatically makes N equal 6 in our formula. Same formula as last time, last problem, but we have to do a little bit of work to find our apothem. So 1/2 times apothem times number of sides times the side length. So we're good with the N and the S, we're just not good with the A. So remember, if you go all the way around the center of a polygon, we go all the way around, that's 360 degrees. We're going to break that 360 degrees up into equal subdivisions based on how many central angles can be created. Well, since a hexagon has 6 sides, if I start drawing triangles out of the center, there should be 6 congruent triangles coming out of the center. So if I take 360 and divide it by 6, that gives me a central angle measurement of 60 degrees. Now, that 60 degrees is kind of handy, except it actually needs to go a step further because the apothem would be breaking that 60-degree angle into 2 equal halves to come up with that perpendicular distance. That's what our apothem is. So then that forces us to really work with an angle that's 30 degrees. So there's a 30 in there. If the entire side length from here to here is 7 units long, we're going to divide that by 2 to get the side length of this right triangle that's been created. So you can call it 3.5. So we're working with a nice little right triangle that has two legs identified. One is 3.5 and another one as with that 30-degree angle. So if I'm looking at setting up a trig ratio that uses the 2 legs, that's what the 3.5 and the A are. The 3.5 is the opposite. The A is the adjacent. So I'm going to set up a tangent ratio. Tangent of 30 degrees is equal to opposite over adjacent. And we have this little trick that we can move things around slightly. I can interchange the A and the tangent of 30 so that A would equal 3.5 divided by the tangent of 30. And let's see what we come up with approximately. So onto my calculator again. Make sure your calculator is in degrees. Mine's not. So let's change my mode to degrees. That will be extremely helpful. And so now if I do, let's see what we're punching in. We're punching in 3.5 divided by the tangent of 30. And I get 6.1 if I go to 1 decimal place, 6.1. That's my apothem. So now I can plug my numbers in and be done. So 1/2 times 6.1 times 6 times 7. And if I punch that all in, one last type in for this problem, 0.5 times 6.1 times 6 times 7. And we get a grand total of 128.1. And that would be in, since there's no other label here, let's go with units squared again. Okay, so that one required a little more work than the previous one because we weren't given the apothem value. Okay, moving forward, beyond our halfway point here, we are finding volumes, and volumes of cylinder. That volume formula is the first one that we'll use. So it starts out area of the base times the height is what you want, but the base is a circle, so I can be more specific, say pi r squared times our height. And we can actually plug values in. So the radius is given to us as being 5. The height is given to us as 9.1. So pi times 5 squared times 9.1. So if I go to my calculator and enter in 5 squared is 25 times 9.1, I get an exact value of 227.5 pi meters cubed. It's volume. If I want an approximation, I just actually take that 227.5, multiply it by pi, and I get to 1 decimal place, 714.7 cubic meters. Okay, nicer problem maybe in the second problem on this page, volume. It's a rectangular box, so it's length times width times height. You really can think about it, area of the base times the height, but length times width times height is probably an older formula that you're aware of. 4 times 2 times 1.5. I won't even pull my calculator out for this one. 4 times 2 times 1.5 should give you a grand total of 12, and that would be labeled in meters cubed. There goes number 9. Okay, so let's keep moving forward. In number 10, The pyramid arena was originally built as a 20,142 seat arena in downtown Memphis on the banks of the Mississippi River. So all nice to know, but not important information for what continues, and the last two sentences are the important ones. It is 312 feet tall, so we have a height. That's our H value. And it has base sides of 921 feet. So understand base sides. This is considered to be a square-based pyramid. So I'm going to even label that as S, as you'll see in my formula in just a minute. Find the volume. So volume formula for a pyramid is 1/3 area of the base times the height. Since the base is a square, I'm going to say side times side, or S squared represents the area of the base. And so if I plug numbers in, 1/3 times 591 squared times 321. And I think we can get an exact value out of this. So 1/3, 1 divided by 3 times 591 squared times 321 for the height. And we get a rather large number there, 37,373,067. And this is all labeled in feet, so it's going to be feet cubed. Okay, check off number 10. So you're going to flip to the back side. We're looking at the volume of a, again, rectangular box, but we have a missing dimension in this volume. We have the length and the width, but not the height. So we're going to go back to that volume formula that we've already worked with. Length times width times height. I'm going to plug in the volume value of 560. I'm going to replace length with 7, width with 8, and the height is going to be the U. So 7 times 8 times U. So 560 is equal to 7 times 8 is 56 U. If I divide both sides by 56, I get a nice value of 10 for that missing dimension, and a great label for that would be feet. So 10 feet for number 11. Number 12, find the volume of the composite solid. So there's a cylinder and a cone put together. So the total volume should be volume of the cylinder plus volume of the cone. So let's write some formulas down for those two. Cylinder would be area of the base times the height, and the base is a circle, so pi r squared times h. The volume of the cone would be 1/3 area of the base times the height, so 1/3 pi r squared times h. Okay, let's see if we can fill in some values. The radius, the 15 that I see for the radius, that would be the radius for both the cylinder and the cone. The 20 I see along the side of the cylinder, that would be the height of the cylinder. The 8 that I see up within the cone would be the height for the cone. Okay, let's see if we can plug those numbers in. So pi times 15 squared times 20 plus 1/3 pi times 15 squared times 8. So 15 squared times 20 is going to give us 4,500. 4,500 pi attached. 1/3 times 15 squared times 8 is going to give me a grand total of 600. Take pi along with that, so we get an exact value of 5,100 pi. And that would be labeled in cubic units, and that would be centimeters cubed. If I want an approximate value, I can take 5,100 multiplied by pi on my calculator, and I get 16,022.1 to 1 decimal place. Centimeters cubed is again my good label on that. Okay. And that checks off problem number 12. Let's move forward to problem number 13. In problem 13, we're looking at the volume, find the volume of Prism B. So we have two similar prisms, so we have to come up with our scale factor. This is a scale factor problem. So scale factor, we always use the variable k to represent scale factor. And we always work with the second object back to the first object. So you're looking for a corresponding measurement between these two prisms. And what's corresponding that's given in each of these prisms are the height. So it's the height of the second divided by the height of the first. So height of Prism B, I'll just abbreviate that as height of B, divided by height of A, that will give me my k value. So it looks like 3/9, and that simplifies down to 1/3. Now, because we're trying to compare and calculate a volume, it's not just k we need, it's k cubed. So we have to take our 1/3 and raise it to the third power. So that's 1 to the third divided by 3 to the third, which should give us 1/3 times 3 times 3 is 27. So k cubed, half of our proportion is going to be represented by 1/27. So I take my 1/27 and I set it equal to, I want the volume of Prism B divided by the volume of Prism A. Well, volume of Prism B isn't known, so I'm going to choose to leave capital B up in the numerator to represent the volume of Prism B. But that's going to get divided by the volume of Prism A, which is the 2,673. So there is a beautiful setup for the proportion. If I do my cross multiplying my calculator, I can take 2673, multiplying it by 1, that doesn't do anything, and then dividing it by 27, and end up with B, capital B, the volume of Prism B, to be 99, and everything's being measured in centimeters. Since it's a volume, make sure it's centimeters cubed. Okay, check off number 13. Moving on to the next problem. How much ice cream can the sugar cone hold if you only fill the inside? So no going overboard, not a scoop on top. And we're going to round this to the nearest centimeter. So rounding to the nearest centimeter. Okay, volume formula for a cone is 1/3 area of the base times the height. The area of the base is a circle, so pi r squared times h. Now we're given all the right dimensions, we're just given an extra dimension that we don't need, so we have to be really careful here. So the 2.1 is our radius. Our height versus our slant height, be careful, we want the height. The height is the 12.21. That should represent our height. So that's what we want to be able to use in order to solve this problem. And let's plug in our values. So volume equals 1/3 pi times 2.1 squared times 12.21. And if I punch that all in and try to get an exact value, I can do the 1 divided by 3 times 2.1 squared times 12.21. It's still going to have a decimal to it, and even a decimal going out to 4 decimal places. I'm going to leave it all there in this case. So 17.9487 with the label of pi, and that would be centimeters cubed Now that's a temporary answer. The approximate answer that I actually want to keep would be this answer rounded to the nearest centimeter. So I actually have to multiply it by pi and then round to the nearest whole number, which would be 56. So the 3 in the 10th position would just keep me at 56 cubic centimeters. Okay, check off number 14. We're on to our last one here. Let's get rid of our calculator. We probably could leave it hanging there too, but a sphere has a diameter, diameter of 11.22. I know the surface area and volume formulas for a sphere both depend on the radius, so we better figure out what the radius is. So the radius is going to be 11.22 divided by 2, and that would give us 5.61. So surface area formula. So surface area, SA or S or A for surface area, 4 pi r squared is the formula. And so 4 pi times 5.61 squared. And if I punch that into my calculator, everything except for the pi, 4 times 5.61 squared, I'm going to come up with 125.88884 pi. If I round it to 1 decimal place, multiply my 125.8884 by pi to 1 decimal place, I get 395.5, and this is all going to be labeled in square feet. Okay, I'm going to let my calculator hang out there. The volume formula for a sphere is 4/3 pi r cubed. So we're going to use the same radius. It just has to get cubed this time. That radius again is 5.61. So if I take 4/3 times 5.61 to the 3rd power, and we get 235. Now it's going out to 6 decimal places, so I actually think it's been, maybe it's not been rounded, so let's just keep it as it is, 235.411308 pi. Okay, and the label on that would be cubic feet since it's volume. And then we can approximate that to finish off the worksheet. So multiply it by pi. And we get 739.6 cubic feet. Okay, folks, that should take care of the review sheet. Good luck with your Chapter 11 test. Thanks for listening today. Bye. Bye.